Hello everybody. Today we'll be asking another question to flat earth people. How do you explain this? Depending on your location, if you measure the acceleration, you put a device that measures the acceleration downwards and you get the results usually in something like meters per second squared, or nanometers per second squared, or gal, which are centimeters per second square. Then you get different values depending on location. And then I got this data from various sources. One is Absolute Gravity, the database by Bureau Gravimetrique International in France, Toulouse. Another source I use, this spans, this is a map with many points of measurements, and we can go for some, like here. Pearl, Cape Town, this is location, height above the mean sea level, and value measured. This one was 20 years ago, and some others are more recent. We can go, for example, to Paris, Severs, get the database entry, and there are hundreds of measurements here. 15 years ago, sure. But you can compare this to many other places, and some are other dates. And yeah, this database has a really good coverage in Europe, some coastal cities in South America, good coverage in Northern America, a bit in Asia and in Australia, and a bit of coast of Antarctica and a few other places. But these are manually done, some are automated actually. Absolute gravity data. Then we have different information, which is in this report from 72, which also measures gravity in different places around the world. So this is, yeah, gives me more places to put the data. For South Pole, I use the data from this page here. I also used Argentinian station in Ushuaia, which is not in this other database. I used here, this one. And I also used some points here. This point. Okay, in Argentina. The reason was there's a band of latitudes that was not covered otherwise. I use information for McMurdo station from some articles. I use this data for Antarctica, which gives me information about the South Pole itself. I only looked at very close to South Pole. This is elevation above the mean sea level. This is a gravitational anomaly. To go back to absolute gravimetric value, I used this formula together with free air correction to get from free air gravity and theoretical gravity to observed gravity, what they actually measured. And I also used a few other articles to fill the gaps. And I got a list of about 112 observations. There's more. I didn't want everything here. I just wanted a good view of all different latitudes. And it's not related to height. If you look at height versus acceleration, it's just random. Even if all the measurements were done very close to sea, they all spread between 978 and 983 meters per second squared. And then, but if you plot acceleration versus latitude, you see the pattern that the ones close to equator are lower acceleration, and ones closer to poles, this is South Pole and this is North Pole, are higher. One thing to note, some of the cities here in the middle are very high and some are very low. So this is why the spread is really high. For example, Bogota, Mexico City, and few other places, they are really high above the sea level. So this explains some of these changes here. The reason why we see these 2 points here at minus 90 is because measured value at South Pole is actually 9.823 from this document, and from other document it is after accounting for the height and anomaly. This gives us this value, but at height of 2,770 meters. Okay, this is very high. If we actually subtract this value with 0.308 milligal per meter, we arrive at this value, which is corrected for the height. Okay, and then we arrive at this point. And yeah, this is something interesting. If we actually take a cosine squared of latitude, then we arrive at this linear function, which clearly tells us that this variation in acceleration is correlated with cosine squared of latitude. And indeed, if you do physical interpretation of rotation and shape of the Earth, the term cosine squared latitude will be there. And yeah, my question would be, why this shape? Why there's a function of latitude? Why the acceleration is dependent on latitude? And again, this is just the acceleration down. This is measured in the past. Actually, still it is sometimes using pendulum in vacuum. It's swinging a little bit. The period can be measured, how long it takes for, let's say, 100 swings, and then we divide by 100. This is pretty precise period. The time can be measured using atomic clock or quartz clock. The length of the pendulum is known from measurement. For some pendulums, pendulums like a bezel pendulum, you don't even need to know exact length between a pivot point and a center of gravity, because it compensates for that using two measurements with reversed. It can be done in vacuum, it can be done in air. The fact that it's fully symmetrical, the air resistance in both reverse and in forward directions are the same, so it cancels out. More precise methods are just free falling. For example, a prism with a mirror or a retroreflector is being dropped in a vacuum tube, and a distance, time and position of this falling prism is measured by computer using laser interferometry to very high precision. We're talking nanometers. Then, because we now know the position in nanometers and time at this position, we will see what is the velocity, how the velocity is changing, and how what is the acceleration. It's very easy to do. The instruments to do it are available commercially. They are not cheap because they are so precise. but they are there. You can buy one with pretty high precision. Some very high-end ones might be, 6-7 digits, but in price. But simpler ones, so-called relative gravimeters, yeah, maybe $4,000, $5,000. Pendulum, probably less. But again, all these tricks, yeah. For our purposes, we only need about 0.1% accuracy, because the difference between minimum and maximum is 0.02, no, I'm sorry, 0.05, and yeah, that's maybe half percent difference. But to have some points that are well defined, we need a precision of 0.1%. The results here are much more accurate. They are about 0.00001%, about a million times more precise than we need to get these results. But we get results anyway. I'm just telling about the measurement methods to give you a context, and maybe you want to replicate this method, for example, at equator, and maybe at Spitsbergen and a few other places. You don't need 100 points. You need maybe just 3 to get idea. The exact shape, it requires more points than that. And yes, and no matter the longitude, only latitude plays the main role here. And the other values, I'm not sure. If I put another column here, and I maybe do a correction of height, which is 0.38 milligal. So this is in gals. It will be 0.00038 gals. This is in milligals, I believe. How we can do this to compensate for height and see if things improve. We know that we wanted to be this in meters per square. So this is in milligals, and this is in meters. So to get from milligals to meter per square, we need to divide by 100,000. 100,000. So 100,000. That's 3.08 and 6 per meter. 308 per meter. So we'll do this minus 308 minus 6 times the height. Oops, A3. This will be corrected to be at level of, is it minus? No, we need to do at plus, because if we are high and now we want to correct to be closer to sea level, we need to add, because we will be closer to the center of Earth. Well, you don't need to, but let's assume this is true and see what happens. We will compute all the values for all the places. This is at height 0, so the value is the same. This one is at 2.7 kilometers, but after compensating, it's the same as at 0. So it looks to be correct. And now we need to do latitude versus this corrected thing. we'll take from D3, from D3, yes, to J3, and we'll customize it. Acceleration latitude, we will do vertical axis to be minimum of 9.73, 24, 28, 27, okay, 9.83, 84, 97, okay, that should be good enough. So this is uncorrected data, and this is corrected data. Okay. And we will do none. And we will also make it from minus 90 degrees to plus 90 degrees. So it's horizontal, minus 90, 90, and add 5, no, this will be 0.01, and a horizontal would be in 5-degree increments. Okay, we have something we can compare. So yeah, this now becomes even closer to model. The very small random deviations here disappear. They are become closer to theoretical model. For example, this point here, we can ask, what is this? This is 3929, 3929, 3929, 3929 is somewhere behind here, 3929. This is a Virginia city, and yeah, it's very high, 2 kilometers above the sea level. So this is why it is, the acceleration is lower. It's further away from the Earth. If we compensate for that, yeah, it's no longer a problem. It's back here. Yeah, it's on a line. There's still some cities here that kind of are not explained by this correction, but the latitude explains it very well, and then correction by height, it makes it even cleaner. If we look at just the height, I believe I have the graph summary here. The height itself doesn't explain anything. There's no relationship between height and acceleration, but latitude does very well. Here, latitude explains this very well, and if we also take into account latitude and then height, it explains it extremely well. So, and this is explained exactly by a globe model. The values I use here for gravity on rotating spheroidal Earth, there are some figures here. These are signs. This is a factor for height above the sea level, mean sea level. And yeah, it explains it well. So Yeah, what is your explanation for that otherwise? Thank you. Bye bye.